First thing isn't really an enhancement. In fact, it's possibly the opposite of an enhancement. We're going to talk about Abaqus CFD and what's happening with that. I'll then talk about Abaqus CAE, the enhancements to the front end, and it's good to see some of those. Then we'll look at some kind of general trends in the Abaqus development scheme. There are some common themes to the way in which the product's developing at the moment. One of those is definitely multi-scale modelling. We'll look at some stuff to do with Contact. Abaqus is all about Contact, and we'll look at what they've been working on in 2016 to enhance the offering in that direction. Some very interesting stuff and some very specific stuff. The ability of Abaqus to do additive manufacturing has been kind of trumpeted and highlighted quite a lot recently. 2017 is the first release where Abaqus users get their hands on the additive manufacturing processes and the additive manufacturing software. So we'll talk a little bit about how that has been rolled out and incorporated in CAE. Then, as kind of is usual in these scenarios, a little bit on material models. There's some new material models that have been developed and are released, something on linear dynamics, and then a new element that has kind of been added to the somewhat extensive family of Abaqus elements. So that's essentially the kind of core subject matter, and hopefully we'll find things that are useful to everybody out there. So the first thing that we want to talk about, and as I said isn't really an enhancement, it's possibly the opposite of an enhancement, is that Abaqus CFD is not available in Abaqus 2017 in the CAE environment. The main direction of development of CFD for Dassault now is in the 3D Experience platform. It's a lot easier to engineer the sort of functionality that you need in a proper CFD code inside that environment. CFD code pre and post processing is a distinct art and a distinct science that's essentially quite separate from the structural world. So 2017 marks the point where CAE is going to concentrate on the structural world, and anything to do with fluids will be incorporated in 3D Experience. There are some really interesting developments in the world of CFD and Dassault anyway, with which people may have heard of the acquisition just before Christmas of the XFlow product range, and that brings some very interesting CFD functionality into the kind of Abaqus SIMULIA family. We're yet to see how that's going to unroll and how that's going to unfurl, but that's a very exciting piece of technology. If you were running Abaqus CFD and you've got projects that you want to carry on using it for, all Abaqus 2017 licenses will run Abaqus 2016, so you'll still have access to the solver. It just doesn't form a part of the CAE 2017 product. So hopefully that's a relatively straightforward point to make. Right, so that's the first kind of like parish notice thing. We'll start looking at CAE enhancements. So here I've screen grabbed Abaqus CAE 2017, and obviously it's quite a familiar thing. Abaqus CAE has been around for a few years now, so you're not going to see any kind of earth-shattering improvements to kind of basic structure and overall look and feel. But the good thing is that CAE enhancements are back on the agenda, and we've started to see functionality added to this environment, and we've started to see support for new Abaqus solver functionality. So as you'd expect, there are numerous small Abaqus CAE enhancements, and they are focused on kind of ease of use, tidying things up, and small speed enhancements, just what you'd expect from Abaqus CAE. But it's really good that we're starting to see Abaqus CAE development back on the agenda. A really good thing and a really good point I'd like to make at this point is that we're going to look at a lot of new Abaqus solver capability, and pretty much all of that capability can be accessed using Abaqus 2017. There are certain areas where that new functionality is command line or input deck only, but all of those functionalities, the support for Abaqus CAE is very, very close to being delivered. So I'm going to just do a quick run through the Abaqus CAE enhancements. As I said, numerous small things all about usability, so consistency checking for regions with section assignments, new set surface queries, geometry and element face normal queries, all sorts of kind of housekeeping, small efficiency changes that everyone wants to see. I really like the idea of relaxed object name lengths, if you could call them mate or something, but really it's about being able to use extended, essentially string length names for objects, which kind of frees up the scope for what you're trying to do. We can also have things like independent datum features. All of these things have essentially been asked for by the customer base. A lot of these are, in fact nearly all of them I think, are in response to enhancement requests that have been made in the last couple of years. So we can go through the list of Abaqus CE enhancements. There are quite a few of these things, and it really signals the fact that product development is now off and going again. So we've got contact controls can be applied to groups of contact pairs. We've got much more with linked viewports. And then we got the last kind of slide full of CA enhancements. So things to do with being able to create steps in ODBs manually. I've actually seemed to have left, can we have an example of rendering and variable thickness shells? Seem to have left that in there rather than actually delivering a picture of it. But we can plainly change the thickness of individual shells using a field, and we can then plot that for visualization and error checking. So as you can see, there's a big list of Abaqus CAE enhancements that are focused on usability and developing kind of the ability to pre and post process the new solver capabilities that are being delivered in 2017. One of the big themes in the world of SIMULIA at the moment is multi-scale analysis. I think everybody who's a finite element engineer is used to different levels of detail in different sizes of model. We could have local models, we can have sub-modeling. So we're already very used to the concepts of multi-scale analysis. The way of kind of direction of travel with SIMULIA is to extend that at both ends. The most specific end that we're kind of working with Abaqus at the moment is a kind of downward scale approach where we're looking at things like representative volume modeling and that sort of kind of multi-scale approach to allow us to model materials in more detail. The whole kind of marketing machine and the real direction of travel with Abaqus is to start looking at molecular modeling with product Biovia. I think it's early days on that, but the direction of travel is fairly obvious with the whole product range. So essentially the multi-scale analysis stuff I'm going to look at now is about extending from kind of simple, in inverted commas, material models to material modeling approaches which allow us to consider combinations of materials that are like composites and fiber reinforced plastics and some biomaterials. And essentially 2017 brings us two approaches for modeling that. We've got a thing called mean field homogenisation. Now, it possibly contains the scariest set of release slides you're likely to see. Mean field homogenisation is a technique that allows us to include essentially something like matrix and inclusions to material system, material distributions, and calculate the behaviour of those under certain loads and displacements. So we have this kind of semi-analytical approach based on defining a unit cell, and we have predefined unit cells defining what those materials are, and then we can come up with a kind of composite material relationship that allows us to use, well, we can use that material definition in the Abaqus solve. So plainly, I'm not going to sit here and go through this stuff, largely because I can't, but if we have a look at the command line inputs for this stuff, you can see that we've got the ability to look at the type of inclusion, whether it's spherical, cylindrical, oblate, whether we can look at the orientations, we can give different material definitions to the matrix in the inclusion, and we can look at things like volume fractions and aspect ratios. So we can define essentially a subscale model of the material to populate or to control the material that Abaqus is going to use. So this is quite an interesting technology and points the way in which the way in which this technology is going to develop. At SSA we've been doing a lot of work with the AlphaStar product. This isn't a kind of AlphaStar level thing yet, but it's certainly heading in that direction. As an FE engineer though, if you were tasked with the idea or the job of calculating what happens to small models of variable material distributions and components made up of multiple parts and material definitions, plainly the way in which you do that is a finite element model. So another approach beyond the kind of Mori Tanaka type of approach we've just looked at is a thing called a representative volume element. RVEs have been around for quite a long time and are quite established in their usage. An RVE allows you to model a subset of the material and then calculate a response which is then used in Abaqus. So RVE technology has been around quite a long time. What is new is the ability to build one of these RVEs, and you build it in exactly the same way as you build any other Abaqus model. You kind of create a material, you mesh it, and then you can use the RVE capability inside Abaqus 2017 to apply periodicity and have a look at the way in which the thing interacts as a whole, and create these material definitions that can be used to populate again or to describe the material model that Abaqus uses to represent what the component level model is doing. So we can link, using Abaqus, we can link the RVE model to the behavior of the overall model. And that, as I say, is something that's part of the 2017 release. You will see things coming along in what they call asynchronous cycles. So because a lot of the interfacing for this is written around Abaqus CAE, you can update using plugins and things to actually exploit this sort of technology. So as I said, all of this stuff sits inside CAE, and you can use it to create these subscale modeling approaches. So that, I think, signals a very interesting technology and a direction of travel, and you're going to see a lot more of this multi-scale stuff as the product line develops. Abaqus, as I've said at the beginning, is a product that is a lot about contact, and as you'd expect, any new release of Abaqus sees development in the contact area. So 2017's no exception in this respect, and we've got a lot of interesting contact enhancements to look at. So the first big ticket improvement to 2017 is that we now have the ability to define cohesive behavior in general contact. I shouldn't imagine that the sticky string problem on the top right was the main motivator for bringing this in. As you can see, all of these things look like technology that's going to be useful in the world of multi-scale modeling. So if we're looking at debonding in kind of granular structures, if we're looking at fiber matrix debonding, you can see that these things start to look like what you'd include in a decent RVE to build up a good damage type picture. So cohesive behavior in general contact has been added to Abaqus standard in 2017. Really pretty example of that, one I really like, is this honeycomb plate. If you look at the kind of general overall picture, it doesn't look that exciting, but when you look at the zoomed in picture, you can see that we built the DS people have built a proper representation of the honeycomb using shell elements, and it's not using a continuous mesh. All of the connections between the cells and the outer skins are created using cohesive contact, and that then allows you some very interesting behavior as we load the thing in extreme situations. Cohesive contact can break down, and we can look at the way in which the thing collapses progressively. So general contact with cohesive behavior sort of frees you up to do some more kind of creative things in extreme situations. Another very similar sort of example problem, and one that kind of follows this theme of RVEs and multi-scale subscale modeling, is this polycrystalline model with uniaxial displacement applied. And you can see that generating this manually, if we had to kind of go in and create contact pairs in this problem, we would be there quite a while, and it's arguable whether you'd ever get anything like this working in a reliable manner if you had to define this stuff manually. We can see that the model's working reliably, and that the bonding has been allowed to occur in the kind of global model. So that is a good example of general contact with cohesives. I couldn't resist putting this slide out. Apparently, it's called "Fun with Cohesive Contact." You can see that this example is using cohesive contact, which is switched to pick something up and drop it off the edge of this plate. So I don't know. Fun might be a bit of a big billing for it. So anyway, beyond cohesive contact in general contact, there's a new linear contact solver. This was first announced in the SEC in 2015, and it allows efficient addressing of a very specific type of contact problem. If you've got a contact problem with frictionless small sliding behavior and there are no other sources of material nonlinearity, then you can use an LCP solver, which will essentially and effectively increase the speed of solution. The first thing that I didn't really notice looking at this slide was that that's a log scale of runtime. So what initially and superficially looks like a small speed up, when you look at it on the log scale, is quite a significant speed up. This speed up is only available in certain restricted scenarios. So if you have a look at that, essentially the problem has to have small amounts of contact in the model. So as long as it's linear and there's small amounts of contact, you can expect a significant speed improvement in the solve times. A kind of word of warning that the DS people have put in the update notes is that you can see that they've shown how when the LCP solver is used in a situation where significant nonlinearity exists in the model, results, to even quote them, are completely different. So as long as the scenario is suitable for the LCP solver, then this contact will offer significant advantages. You don't have to use it, but it's there if your problem is kind of suitable. Another contact example, another contact enhancement, thick beam contact. We've always been able to do beam to surface contact, or certainly recently it's been available technology. 2017 allows us to use the thick beam as the master, and the important and the interesting thing about this functionality is that if we twist the beam, if we impart a rotation to the beam, it can then transfer that rotation to shell elements or surfaces and transfer that motion, which is a kind of new functionality which is useful in a number of scenarios. So then we're on to CZone. You may or may not be aware of CZone as a program. CZone is a product that has been developed and been available for a number of years now, that allows you to handle the fact that in a crash situation, composite materials generally tend to just degrade very rapidly and very locally in the contact region. So CZone essentially is a contact functionality that takes energy out in the contact region, deleting elements in the contact zone, allowing you to simulate the sort of thing that you see in an automotive composite crash scenario. So that functionality has been available for a number of years now and been very successfully applied in lots of situations, but in previous versions CZone required you to use contact pairs. 2017 we can use general contact, which means it's now further in kind of further into the Abaqus solver. It's more kind of an intrinsic part of what's going on, and therefore we have a number of advantages to do with model setup and some to do with performance and parallelization in these very computational heavy composite crash scenarios. As you can imagine, these things don't run hugely quickly. So here's a few example problems that basically highlight the benefits of general contact. I think most people are up to speed on the overall benefit of general contact itself, and when we've applied that to CZone, you can see that you get those benefits. So that's essentially tidied up and improved the usability of the CZone product. XFEM is an interesting technology that most people are probably aware of. It's a technology that allows you to simulate cracks growing through meshes without the kind of headache of continually remeshing and redescribing the problem. So XFEM is a very interesting technology. Plainly, as you generate a crack in a piece of material, you're going to create exposed surfaces, and the big update in 2017 is those exposed surfaces can now take part in contact relationship, in contact scenarios. So as we expose an edge of the surface, that can then take part in a general contact model. So that provides quite an enhancement to that sort of technology. The big application of that is in fracking. Fracking is variably popular, I imagine, but the application of all this new XFEM technology is to allow fracking models to be generated and solved. So another contact enhancement, anisotropic friction. We can have different frictions in two different directions. An obvious application of that would be in crash modeling of seat belts, and you can see in this fairly simple example that the anisotropic and isotropic friction results have given the solution a different look. So that is another 2017 update. You may or may not have used smooth particle hydrodynamics in Abaqus. It's a very interesting, very useful technology with some very specific applications. Tidying up the boundary behavior and the contact behavior of SPH and optimizing it has been a kind of work in progress for a number of years with the Abaqus solver. The significant improvement that we're looking at in 2017 is that they've essentially suppressed the tendency of SPH particles to interact with each other through a wall. So in 2016, you can see that in the example here, we've got one set of SPH particles at the top, another set at the bottom, and a wall in the middle. If you move the bottom row, the top row are moving along in kind of unison to some extent. That is an entirely non-physical behavior, and in 2017 that doesn't happen anymore. What does that look like in a real example? If we look at this kind of sloshing baffle example, you can see that we've got more physical behavior and a distinctly more sensible, more physical velocity distribution in this sloshing example. So I guess the important thing with SPH is with every release that the solutions become smoother, more physical, and more representative of what really goes on. I'm not entirely sure whether anyone in the SSA user community has built the EM model yet. DEM's really interesting technology, largely, well, as the name, I don't actually say what the name is there, but discrete element modeling. It's about modeling discrete lumps of material. You can see three examples here. One which is the kind of classic rock sorting example, another one a kind of mixing example. There have been numerous speed and functionality improvements to DEM, which is relatively new to Abaqus, maybe the last couple of releases, so it's in the phase of development where you're likely to see these things happening. So something that we've been putting a lot of effort into at SSA, and something that I personally are very interested in, is additive manufacturing, process simulation. This technology has been marketed and talked about extensively over the last year, 18 months, and 2017 is the first year that this technology, or the first release of this technology, is generally available. The good thing about additive manufacturing process simulation is that Abaqus is incredibly well set up to perform these sort of simulations. We're looking at thermal effects, we're looking at nonlinear materials, we're looking at large strains. All of these things are things that Abaqus does well. So the development of an AM process simulation functionality is an obvious thing to have done, and basing it on core Abaqus functionality means that it's reliable and useful. So there are essentially two distinct strategies required to model additive manufacturing processes on top of what you can do in standard Abaqus, and one of those is to model the addition of material in very, very much the way in which world simulations have been done previously. So we can use some form of field control to switch on elements using element properties. So this is a slide from a presentation I did a number of months ago. So essentially we have to add material. That in 2017 is called element progressive activation, and you could always do world simulations using model change. This is a finer control that allows us much more precise modeling of the additive manufacture process. So we have a number of star inputs. There will be CAE enhancements fairly soon that will allow you to do this. Currently you have to do it using scripting. Another function of the additive manufacturing process that is kind of critical and not possible with a standard copy of Abaqus is to essentially model the fact that as we add material, the boundary of the model changes and the thermal losses and the thermal problem changes with the build. And so we need to be able to lose heat from the evolving surface. In Abaqus 2017, these are handled using two new commands: free surface convection, which is obviously the convective loss from the new built surface, and free surface radiation. So we can handle the heat losses from those evolving surfaces. Obviously, a lot of heat loss goes through the build plate, and that is obviously going to be just a standard conductive heat loss. As I said, these are currently supported by scripting and input file only, but very soon they'll be supported by an enhancement to CAE that will almost certainly be released in an asynchronous manner. We won't have to wait until 2018 to get that. There have been a number of material model enhancements, as you'd imagine, from Abaqus. They've added a number of functions: multilinear kinematic hardening, nonlinear damage initiation for ductile materials, rate-dependent cohesive behavior in Abaqus Explicit. We've got LARC composite failure model added. We've got enhancements to the PRF model, and if ever there was an underused piece of technology, it would be the parallel rheological framework, which is a really, really important piece of technology if you're modeling plastics and polymers and time dependency. And then again, in that essential same technical ballpark, we've got a structural relaxation model that have been added. So I count 6 additional material models in the 2017 Abaqus release. So it's always good to see a new element. 2017 has a new 3D solid element, and it's essentially something that builds on the 3D continuum shell element. 3D continuum shell element was something that for me kind of almost revolutionized my approach and my view on 3D modeling and how you do things using shell elements. And you may remember I did a webinar on that a number of months ago, maybe a couple of years back. So the 3D continuum shell element was a great thing, but it didn't have full 3D behavior through thickness. It had a plane strain behavior. Sorry, I was absolutely guaranteed to get that wrong. As a plane stress behavior through the thickness. The new brick shell element, CSS8 element, has full 3D behavior through the thickness, which kind of improves its accuracy. It's a better element, and as you'd imagine, is well suited for modeling composite solids. It's only available in Abaqus Standard. Seem to have managed to put the thickness direction in a fairly odd place. So basically, you use it very much in the same way as you'd use a continuum shell element, but the CSS8 doesn't support stack direction parameter in solid section, so that when you build this models using this element, you have to make sure that you're going to get the right thickness direction. It's the easiest thing in the world to build a model using these sort of elements where you get it 90 degrees out of kilter and things don't work well. So it's very important in that element to work out that you've got the stack direction right as a function of the way in which you built the model. Easy enough to do, but also easy enough to forget. So as is also usual in an Abaqus update, they've done a lot of work on linear dynamics, a lot of it based around the modal superposition solver. So we've got performance enhancements and we've got scope enhancements. As I said, with all of this sort of stuff, there is a lot of detail in these releases, and perhaps not a webinar is not the best environment to kind of go through these things. So if anyone wants more detailed information on these enhancements, then plainly at the risk of causing upset, it's in the documentation, but also we've got a presentation material if anyone wants to get hold of it. So as I said, lots of development around linear dynamics, which again points to a kind of improved or an increased amount of usage in Abaqus for that sort of scenario and that sort of solution. So in summary, 2017 is increasingly looks like a very important release. There are a number of technical themes around multi-scale modeling, around enhancements to contact, and there are a number of other themes. And the significant point that I hope comes out of this is that we're starting again to see developments back on the CAE interface, which most Abaqus users tend to use. So there is a roadmap for continuing that development, and that I think is very reassuring to people who use CAE as their core pre and post processing software. There have been significant solver enhancements in 2017. There's a lot of science there's a lot of physics, and there's a lot of solver development, and that is a very, very good thing to see, and points to a product that's being actively developed as a solver engine. And those developments, contrary to a viewpoint that many people may have kind of developed over the last couple of years, all of these solver developments we've talked about are available in the CAE environment to a traditional Abaqus user, and that is a good thing and a good point to take home. So I'd like to thank everybody for their attention and listening in on this webinar, and I'd just like to point out that if anyone wants the presentation material, it's all available, and I think all you need to do is email info@ssanalysis.co.uk and we'll send it out to you. So at that point I'll finish up, and thank you very much for your attention.